Welcome back to The Deep Dive, the show where we take those incredibly dense technical documents and turn them into something you can actually use.
Yeah, we're talking about the ones with all the acronyms and equations that usually just gather dust.
Exactly. And today we are putting on our hard hats. We are diving deep into the world of biopharma manufacturing.
It's a high-stakes, high-pressure environment.
It really is. We're focusing on microbial fermentation, specifically the real workhorse of the industry, recombinant E. coli.
Right, the bacteria we use to make all sorts of critical things, like vaccine antigens.
And this is where the central challenge lies, isn't it?
Yeah.
This immense pressure to maximize your yield, your titer, but at the same time, you're fighting against the fundamental biology of the organism. It's this incredibly delicate dance.
It is. And today we're talking about what happens when that dance goes wrong, horribly wrong.
We're talking about the absolute nightmare scenario, the silent killer of fermentation batches, acetate accumulation.
They call it carbon overflow metabolism in the field.
And this isn't just, a small dip in your yield. This is about multi-million-dollar GMP good manufacturing practice failures.
Failures that can stall an entire clinical pipeline. We're talking catastrophic waste, regulatory nightmares.
So to get to the bottom of this, we're drawing from some really specialized source material today.
Yeah, this is a training manual for fermentation scientists. It's built around, a pretty brutal real-world case study.
A case study of a recombinant E. coli vaccine process that just failed spectacularly.
Right at the pilot scale.
Yeah.
And it forced a complete rethink of the entire process.
What I love about this source is the sheer experience it captures. It's over 15 years of insight.
And it bridges that infamous gap between, a perfect run in a 10-liter lab vessel and the chaotic reality of a 100,000-liter commercial reactor.
That's our mission today, to pull out those practical, battle-tested lessons from that exact gap.
We need to understand not just the mechanics of why it failed, but the deeper reasons. Why do problems that are basically invisible at the bench scale become these multi-dimensional disasters when you scale up?
It's not just biology.
Oh, not at all. It's engineering, it's control systems, it's even human factors. You have to look at everything.
Okay, let's unpack this. What exactly is happening inside that cell when it gets stressed and the whole system just goes into this metabolic meltdown?
So we have to start with the core mechanism. It's called overflow metabolism.
Okay.
In any high-performance fed batch fermentation, the whole game is about balance. You're constantly feeding a carbon source, usually glucose, into the tank.
And the goal is to keep the cells in that really efficient aerobic state, right?
Yeah.
Where they're using oxygen to burn that fuel cleanly.
Precisely. You want them happily running what's called the tricarboxylic acid cycle, or TCA cycle. Think of it as this perfect little biochemical furnace that gets the most energy possible out of the sugar.
Right. Maximum efficiency.
Exactly. But the whole problem of overflow comes from what we call a kinetic mismatch.
A mismatch.
Yeah. The cell's machinery for pulling in glucose is just incredibly fast. It can absorb the sugar much faster than it can actually process it through that efficient TCA cycle.
So it's like a traffic jam on the metabolic highway.
That's a perfect analogy. It's a traffic jam.
Yeah.
And the cell has to do something with all that excess traffic, which in this case is a molecule called pyruvate.
I like thinking of it as a funnel. You're pouring water, the glucose, into the funnel faster than it can drain through that small hole at the bottom, which is the TCA cycle's capacity.
Yes.
Eventually, the funnel overflows, and the water spills out everywhere.
That is the perfect visualization. The spillover that diverted traffic is pyruvate. Instead of going down the efficient aerobic path, it gets shunted off onto these much less efficient side roads, fermentative pathways.
And the result of that detour is acetate.
The immediate and very toxic result is a massive buildup of acetate.
Now, you said this gets even worse in recombinant E. coli, especially when they're making something really complex like a vaccine antigen. Why is that?
It's because you're adding this huge metabolic burden on top of an already delicate system.
Okay.
When you force an E. coli cell to spend enormous amounts of its energy and resources making a foreign protein, its central metabolism is already under a ton of pressure. It's like it's trying to run a second factory inside itself.
Like trying to win a marathon while carrying a 50-pound backpack.
Precisely. The cell's overall ability to handle glucose efficiently is already compromised, so it hits that overflow limit, that traffic jam point, much, much sooner and at lower glucose levels than a normal strain would.
So making acetate just becomes the path of least resistance.
It's the only path left when the main highway is clogged with all the machinery needed to make that antigen.
So let's quantify this. What are the measurable symptoms of this disaster? Let's start with the biology.
The symptoms are swift, and they are incredibly destructive. The single best indicator is the specific growth rate, which we call mu.
Right.
In a healthy process, you're aiming for a robust mu, maybe around 0.35 inverse hours. When acetate toxicity hits, the source material shows it just crashing.
Yeah.
We're talking down to less than 0.1.
Wow. So the cells basically just stop growing.
They effectively stop all efficient growth and division.
Yeah.
They're just trying to survive.
And if they're not growing, that means all that expensive glucose you're feeding them is just being wasted.
Absolutely. You see a direct crash in what we call the biomass yield, or Y-axis. That's the grams of cell mass you get per gram of glucose you put in.
And how bad is that drop?
It falls from a healthy 0.5 grams per gram all the way down to a miserable 0.3.
So 40% of your main carbon source just went into making a toxic waste product instead of your actual product.
Exactly. It's just gone, turned into poison.
And the ultimate pain point for any company, the product titer, the actual amount of vaccine antigen they can harvest.
That's where you see severe losses. The manual reports numbers in the range of a 40 to 50% loss of the target antigen.
Half your product is just gone.
Gone. Which means the batch is a regulatory failure, period. It doesn't matter if the cells survived, you missed your target. The batch is a write-off.
Okay, so that's what's happening to the cells. Now, let's switch to the control room. I'm a process engineer. I'm watching my screens. What am I seeing that screams crisis?
You're watching for three main things. First, the obvious one. Your offline samples come back and show acetate levels hitting those critical thresholds, maybe 5 to 8 grams per liter.
Right, the direct measurement of the poison.
The second one, and this is the one that always trips people up, is you start seeing these erratic spikes in the dissolved oxygen, or DO.
Yeah, that is so counterintuitive. If the cells are struggling, shouldn't the oxygen level be dropping, like they're gasping for air?
Logically, you would think so. But you have to remember what the DO probe is measuring. It's the balance between the oxygen you're pumping in and the oxygen the cells are consuming.
Their oxygen uptake rate, or IR.
Exactly. And if the cells are poisoned by acetate, their aerobic machinery shuts down. Their IOR plummets. They literally stop breathing.
So consumption stops.
And when consumption stops, the amount of oxygen dissolved in the liquid skyrockets. You get these sharp DO spikes, even while the engineers are frantically cranking up the agitation, trying to force more air in.
It's the sound of silence in the bioreactor. The cells have just given up.
That DO spike is the classic signature of a metabolic crash. And the third indicator you'll see is just time.
Time.
Yeah. All the things the engineers do to try and save the batch backing off the feed, adjusting pH, it all just lengthens the run. Often by 12, even 18 hours, it completely destroys the manufacturing schedule.
So let's talk about the bottom line. The source mentioned a figure of $50,000 per failed run.
Right, and that's just the cost of the raw materials, the media, and the plant's operational time, which is significant.
But that's just the tip of the iceberg, isn't it?
Oh, it's a tiny fraction of the real cost. The cascading pain is far, far worse. A GMP batch failure means that material, which was destined for human clinical trials, has to be thrown out.
And then comes the investigation.
A failure investigation that can take weeks, tying up your best people. But more importantly, as this case study showed, repeated failures just halt your clinical development timeline. A 6-month delay in getting a new vaccine to market can mean billions in lost revenue.
So that $50,000 is nothing.
It's a mosquito bite compared to the regulatory and commercial hemorrhage that follows.
Which really drives home the point that a biological failure like this is almost never just a biological problem. It's an engineering problem or a control problem in disguise.
Absolutely.
Which brings us to the core question. Why did this process, which ran perfectly in a 10-liter lab fermenter, fail so catastrophically at 1,000 liters?
This is where you need that multidimensional, what we call a fishbone diagram analysis, because a simple superficial fix is doomed to fail again.
The central paradox is that the assumptions you make in the lab, perfect mixing, uniform temperature, instant sensor response, they're all completely false at large scale.
The lab is a perfect little bubble. The pilot plant is a massive, chaotic physical system. And we have to dig into how that lab model breaks down.
So let's start with the biological and physical interactions. It's not just about the metabolic burden.
No. The source material points to two other key things. One is plasmid instability, which is a known issue. The cell is always trying to get rid of that foreign DNA.
Right.
But the other one is fascinating. Physical shear damage.
You mean the impellers, the big mixers in the tank, are physically hurting the cells?
Yes. At 1,000 liters, the impellers are huge. They have to be to mix that volume. And they generate significant local shear forces that can physically damage the outer membrane of the E. coli.
And what does a damaged membrane do?
It reduces the efficiency of the specialized channels, the porins, that transport glucose into the cell. So if the cell is physically damaged and can't get its food efficiently, it's forced into those fermentative acetate-producing pathways much earlier. The physics of the reactor is directly undermining the biology.
That is a profound link. The mechanics are causing metabolic shifts, which leads us right into the engineering factors. This seems to be the biggest failure point.
It absolutely is, and it boils down to two killers: oxygen and mixing. First is the massive drop in oxygen mass transfer efficiency, which we measure as K.
And the numbers in the source material are just shocking.
They are. In the lab, you can easily get a K of 200 inverse hours. It's incredible. But at pilot scale, that number crashes. It drops to maybe 80 or 100.
So you've just cut the cell's oxygen supply in half.
Effectively, yes, by 50 or 60%. And when you do that, you create what are called microaerobic zones.
Pockets of low oxygen in the tank.
Exactly. And they often form right where the glucose feed is being pumped in. So the cells get hit with a huge dose of sugar in a place where there's no oxygen. Their only choice is to ferment it.
And that creates a localized burst of acetate that then poisons the whole tank.
You got it. And this isn't just an oxygen problem, it's a mixing problem. Which brings us to power input, or PV.
Power per volume. How much energy you're putting into stirring the broth.
Right. In the lab, PV is really high, 5 to 7 kilowatts per cubic meter. You get perfect instant mixing. At pilot scale, it drops way down, maybe 1 or 2 kilowatts.
What does that feel like inside the tank?
It feels like you're trying to stir a 1,000-liter vat of molasses with a tiny coffee stirrer. You just can't homogenize it.
And that creates substrate gradients.
Acute ones. The concentrated glucose feed gets pumped in and it doesn't disperse. It creates these temporary hot spots of super high glucose concentration. Any cell that passes through that zone is overwhelmed and instantly starts making acetate.
So the engineers are fighting a losing battle against low oxygen and these local glucose spikes. Let's move to the control strategy. The sensors and systems themselves.
This is the hidden killer. The lab models all use these perfect, ideal exponential feeds, assuming they get instant feedback from the system.
But at scale, you have to deal with probe lag.
Exactly. In the lab, your DO probe might respond in under 30 seconds. At 1,000 liters, that lag can be 2 to 5 minutes.
5 minutes.
It's just physics. The time it takes for the liquid to circulate to the probe's membrane to react. So if your control system takes 5 minutes to realize it's overfeeding glucose, it's already been overfeeding for 5 minutes. That cumulative error is what triggers the acetate disaster.
And if they're only looking at DO, they're missing the real story.
They are flying blind. The moment the cell switches from healthy aerobic metabolism to overflow, you see it in the off-gas. The ratio of ROR to CER, oxygen uptake to carbon dioxide evolution. Without that real-time monitoring, you only see the problem after the culture is already poisoned.
Okay, let's step outside the reactor itself. What about raw materials and utilities?
Even small variations here can completely destabilize a process. The source highlighted trace metal variability in the glucose feedstock.
Trace metals.
Yeah, things like copper, zinc, iron. They're essential cofactors for critical metabolic enzymes. If your glucose supply has a 10 or 20% lot-to-lot variation in these metals, it throws off the cell's internal regulation.
So a different batch of sugar could actually cause a different metabolic outcome.
Precisely. It directly impacts the enzymes needed for that clean aerobic pathway, making acetate formation much more likely. Your raw material quality becomes your biological stability.
And then there's the plant infrastructure itself. How can something like steam quality cause a metabolic failure?
It's all about temperature control. Enzymes work in a very narrow temperature band. If the quality of the steam that heats the reactor jacket fluctuates, you can get these temperature gradients inside the tank. Maybe plus or minus half a degree Celsius.
Half a degree doesn't sound like a lot.
It's huge at the enzyme level. That small shift is enough to destabilize a key gatekeeper enzyme called phosphofructokinase, or PFK.
And what does PFK do?
It's one of the main control points for how fast the cell consumes glucose. If you destabilize PFK, it's like leaving the front door of the glucose pathway wide open. The cell starts eating sugar uncontrollably, which forces a massive immediate overflow to acetate.
So a problem with a boiler in another room can poison the batch?
That's the perfect illustration of why this has to be a multidimensional analysis.
Which brings us to the last piece. The human and organizational factors.
These are often the root cause of the technical failures. The source points directly to rushed clinical timelines.
Right.
Management pushes to go faster, so teams skip critical validation steps, like using small-scale simulator systems to predict these gradient problems. They prioritize speed over engineering rigor.
And you get silos. The R&D team and the manufacturing team not talking to each other.
It's endemic. R&D develops a great strain, then just throws it over the wall to manufacturing. They don't communicate why the strain is so sensitive, or manufacturing ignores data from previous campaigns. They just assume the process is robust when it's actually balanced on a knife's edge.
So you have this perfect storm. A stressed biological strain, a failing engineering system, slow controls, variable raw materials, and a rushed, fragmented organization.
The recipe for disaster.
Let's see how that recipe played out in the real-world case study.
Right. So this case study is it's a perfect roadmap for how these things happen. The product was a critical vaccine antigen for a respiratory pathogen made in recombinant E. coli.
And the scale was 1,000 liters, under full GMP clinical standards.
The pressure was on, and the outcome, as we said, was total failure. Batches were failing release because of acetate toxicity. Titers were stuck at 1.2 grams per liter, which was only about half of what they needed.
So what was the initial reaction from the team when this happened?
The initial sort of knee-jerk reaction was to blame the bug. The R&D team immediately started looking at internal strain tweaks, genetic modifications, trying to make the E. coli more robust.
So they were trying to solve what sounds like an engineering problem with a biological solution.
Exactly. And they wasted weeks doing it. They were completely ignoring the mountain of operational data that showed the feed ramps were totally misaligned with the cell's actual metabolic rate, the AUR and CER data.
They just assumed the tech transfer was perfect.
They assumed the perfect mixing they saw in the lab just existed at 1,000 liters, which was completely false.
How bad was the bottleneck from that decision to blame the genetics first?
It was catastrophic for the program. They had 3 consecutive batch failures that delayed their IND, their investigational new drug application, by 2 full quarters. 6 months.
Wow.
The pressure was immense. The CMO, the contract manufacturer, actually halted all production. The project was dead in the water.
So what was the turning point?
The turning point was when they finally brought in external consultants. And the first thing the consultants did was call a functional review meeting.
Okay.
And they made one rule for that meeting. I was talking about genetics. They focused purely on the process data, the engineering data, mixing power, gas exchange rates, probe response times.
They looked at the physics, not the biology.
Exactly. And that review immediately pinpointed the core cause. A feed kinetics mismatch driven by poor oxygen transfer and that deadly control loop lag. The strain was fine. The process was killing it.
Such a clear lesson.
Yeah.
Always suspect the process before you blame the strain. So once they knew the real problem, what did they do to fix it?
The solutions were comprehensive. They had to be. They basically overhauled the entire process, focusing on stabilizing the kinetics and fixing the physical environment of the reactor.
Let's start with the kinetics, the feeding strategy.
This was the biggest change. They moved away from that timed, pre-programmed exponential feed.
Which was doomed to fail because of the probe lag.
Right. They switched to something called diostat control. This is a feedback-driven strategy.
How does that work?
It's actually pretty elegant. The system was programmed to only pulse in a small amount of glucose when the dissolved oxygen level rose above a set point of 30%.
So a high DO reading was the trigger to feed. Walk me through that logic again.
If the DO is high, it means the cells aren't consuming much oxygen. And that's usually because they've run out of glucose to eat. So the high DO is a signal from the cells saying, hey, we're ready for more food.
It perfectly syncs the feeding to the cell's actual real-time metabolic demand.
Perfectly. It limited the substrate uptake to a safe, controlled rate, and it completely prevented that overflow condition. Acetate levels just plummeted.
Okay, so that fixes the control side. What about the physical engineering problems? The bad mixing and low oxygen?
For that, they had to do an impeller swap. They replaced the old system with a dual impeller setup, a Russian impeller on the bottom and a marine impeller on top.
2 different types. Why?
They do 2 different jobs. The Russian impeller is a high shear design. It's fantastic for chopping up air bubbles and maximizing oxygen transfer. The marine impeller is designed for bulk fluid movement, for creating that top-to-bottom flow that eliminates gradients.
So one for oxygen, one for mixing. How did they know it would work before they spent all that money?
This is where modern tools come in. They validated the new design using computational fluid dynamics, or CFD modeling.
Future simulations.
Right. They built a virtual model of the tank and the new impellers and simulated the fluid flow. The CFD model confirmed they'd get a huge boost in coli, up to 150, and that they would eliminate those deadly substrate gradients near the feed port.
And they also brought in some pretty sophisticated process analytical technology, PAT.
They did. This was about moving from being reactive to being predictive. They installed a Raman spectroscopy probe.
And what does Raman do?
Raman is amazing. It uses a laser to measure in real time the concentration of multiple things at once, glucose, acetate, biomass, directly in the broth. No more waiting 4 hours for an offline sample.
So you're getting instant data. How did that change the control logic?
It allowed for true predictive control. They programmed the system to automatically cut the feed rate if the Raman probe detected acetate starting to creep up above just 1 gram per liter.
So they were intervening at 1 G per L instead of finding out at 5 or 8.
Exactly. They were stopping the problem before it could even begin.
And the last fix was a change to the very beginning of the process, the seed train.
Right. This was about preparing the cells for the main event. They extended the seed culture hold time by 4 hours and gave the cells a very small, low-glucose pre-feed during that time.
What was the goal there?
The goal was to acclimate the cells and, more importantly, to prime the TCA cycle enzymes. By giving them a little taste of glucose ahead of time, their aerobic machinery was fully fired up and ready to go when the main fed batch started. It completely cut down on those initial acetate spikes.
These all sound like fantastic solutions, but they don't happen in a vacuum. There are always trade-offs, right? Especially with cost and time under GMP rules.
Always. You're constantly balancing CapEx versus OpEx, capital expenditure versus operational expenditure.
So the impeller swap, for instance, that's a big capital expense.
It is. The source estimates around $50,000 for the hardware and installation. That's a significant upfront investment. But that one-time $50,000 CapEx cost prevents dozens of $50,000 OpEx losses from failed batches. It's the best insurance policy you can buy.
And what about the PAT system, the Raman probe? The cost there isn't just money.
No, the cost is time. In a GMP environment, any new analytical tool has to go through months of rigorous IQ/OQ validation.
Installation and operational qualification.
Right. The source notes that this validation process added 4 to 6 weeks to the project timeline. You have to be willing to trade that time for the reliability and compliance the new system gives you. Unreliable data is worse than no data at all.
It really shows that the most elegant science still has to get approved by the accountants and the regulators.
Every single time.
So the ultimate goal of this entire painful process is to learn from it, to build a mental model so this never happens again.
Exactly. And the guidance has to be different for the team in the R&D lab versus the team on the manufacturing floor.
Okay, let's start with the lab scale R&D folks working at that 1 to 10 liter scale. What should they be doing differently?
Their mission has to be to stop assuming everything is perfect and uniform. They have to start trying to simulate the heterogeneity of the big plant.
How do you do that in a small lab vessel?
You use advanced parallel systems like Amber or Dasket bioreactors, and you deliberately stress the process. You vary the agitation speed way outside the normal range, you test different feed port locations, you try to break it. If it crashes under simulated poor mixing, it is not ready for tech transfer.
And how can they spot the acetate problem earlier in those small systems?
They have to look beyond just OD, the optical density measurement. OD only tells you if you have cells, not if they're healthy.
Right.
The real early warning sign is in the off-gas. You monitor the ratio of CER to hour. If that ratio climbs above 1.2, that is a huge metabolic red flag.
Why is a ratio over 1.2 the magic number?
Because in perfect aerobic metabolism, you produce about 1 molecule of CO2 for every molecule of oxygen you consume. The ratio is 1. When it starts climbing, it means the cell is making extra CO2 from fermentative pathways. It's a direct sign that acetate production is starting.
So you see that spike, you immediately run an HPLC sample to confirm.
Immediately, every 4 hours, not just the end of the run.
They should also be intentionally stress testing the kinetic limits.
Yes. Do a pulse test. Deliberately give the culture a 2 times glucose spike for a couple of hours and see what happens. If it handles that overdose without making a ton of acetate, you have a robust process. If it crashes, you know your operating window is dangerously narrow.
And the source has a really deep insight about plasmid burden.
This is the key technical takeaway for R&D. That metabolic burden from making the foreign protein is subtle. It stresses the cell's internal energy state. Specifically the ratio of NADH to NAD plus...
A ratio that standard models completely miss.
Completely. So the lesson is, Plasmid burden hides in models. Use metabolomics for NADH insights. If you use metabolomics to see that that energy ratio is out of whack early on, you know a metabolic crash is coming, even if the OD curve looks perfect.
Okay, now let's switch to the pilot and commercial scale teams. What's the guidance for them?
For them, it's about physical reality. They should retrofit the feed lines for bottom-fed glucose, putting the feed port right near the impeller where there's maximum turbulence to get instant mixing.
But they also have to be realistic about the plant's limitations.
You have to be. You can't just demand more air. You might have to cap your airflow at 1.5 VVVM because that's all the plant compressor can deliver. You have to optimize your antifoam use because too much of it kills your oxygen transfer.
And they have to accept that the process will just be different at scale.
100%. The most important thing is to de-erate the feeds. You take the feed rate that worked perfectly in the lab and you reduce it by at least 15% to start. You have to accept that everything at scale is slower and less efficient. You design for robustness, not for speed.
This whole experience seems to boil down to 5 really powerful, hard-won lessons. The final mental model.
It does. And the first is that shear and thresholds are linked. The toxic threshold for acetate isn't a fixed number. High shear from a big impeller damages the cell membrane and changes how it takes up nutrients.
So the amount of acetate that was safe in the lab could be toxic in the pilot plant.
Exactly. You have to revalidate those thresholds at every scale.
The second lesson is about automation.
Right. Control loop instability is inevitable. The PID loops you tuned perfectly in the lab will go crazy at commercial scale because of that probe lag.
So what's the fix?
You have to add dead time compensation early in your control software design. You program the system to anticipate the lag so it doesn't overreact and cause these wild oscillations.
The third one is that reminder about the plasmid.
Yes. Don't forget, plasmid burden hides in models. Use metabolomics for NADH insights. Always check the cell's underlying energy state.
And the fourth is a huge warning about rushing.
It's a warning every project manager needs to hear. Skip intermediate scales and GMP rushes at your peril. That intermediate pilot scale isn't just for testing the biology, it's for stress testing the facility's utilities.
The steam, the cooling, the condensate.
All the things that are hidden in small systems but become massive bottlenecks at large scale.
And finally, a reality check on fancy new technology.
PAT is critical, but it's not foolproof. Raman is precise, but it can drift. The key is PT redundancy. You back up your complex Raman analyzer with a simple, robust measurement like off-gas analysis. You always need a fail-safe.
So this was a huge, expensive intervention, but the results seem to have completely transformed their process.
They were financially transformative. Let's look at the numbers.
Yeah.
The titer, the amount of product, went up by 60%. They went from a failing 1.2 grams per liter to a consistent 2.2.
So they were finally hitting their clinical targets.
Hitting and exceeding them. And the yield, the efficiency, also soared. They were getting 50% more product out of the exact same amount of raw materials.
But in GMP, the most important metric is often just reliability, consistency.
And the reliability gains were staggering. The batch failure rate dropped from a catastrophic 30%.
Almost 1 in every 3 batches was failing.
Right. It dropped to less than 5%. And the batch-to-batch consistency, the coefficient of variation, tightened from 25% down to a rock-solid 8%. That's the kind of number regulators love to see.
And all of that must have saved a massive amount of money.
It did. By stabilizing the process, the overall fermentation cycle time was cut by 15 hours. When you add it all up, higher yield, fewer failures, faster cycles, the overall cost per kilogram of product was reduced by 35%.
Wow.
It turned a high-risk, high-cost process into a scalable, commercially viable platform.
So summarizing the big picture impact here, how does solving this acetate problem address the major bottlenecks in the industry?
It hits the biggest bottleneck of all, scale-up risk mitigation. The lesson is that you can't just engineer a better strain of E. coli. You have to engineer a better process around it. You have to use robust engineering and control systems to manage the biological complexity.
And that de-risks everything down the line.
It de-risks the entire development pathway. By controlling this overflow metabolism, you unlock the full genetic potential of your strain. You get the high titers you need, you cut your manufacturing costs, and you get critical medicines to patients faster.
What a journey. I mean, we went from the physical limits of a 1,000-liter impeller all the way down to the stress on a single enzyme because of a fluctuation in the utility steam.
It really shows you have to look at everything. The solution required organizational change, capital investment, rigorous validation, all of it.
And the core mental model seems to be You have to anticipate failure. You stress test your process, and you build redundancy into your controls.
The biggest failures always happen at that chaotic intersection where the biology meets the pipes, the mix ingredients, the control lags. Engineering rigor is the only way to navigate that.
So what does this all mean for you?
It means that if you're in bioprocessing, your real job is to be a kinetic detective. You have to anticipate how the physics of the plant will break the biology and design your system to prevent it. Never, ever trust an assumption you made at the lab bench once you cross that 100-liter line.
And we want to leave you with one final provocative thought today, building on this. If managing acetate in E. coli required us to understand shear-induced damage to the cell membrane at a molecular level, those porin changes, what other invisible non-metabolic stresses are limiting our more advanced mammalian cell cultures, like CHO cells, when we scale them up?
Where else are we failing to revalidate our basic kinetic assumptions? The solution to getting that next level of productivity is probably not in the cell's genetics. It's in perfecting the physics of the tank it lives in.